Okay, let's continue from where we left. Do you have any question? Okay. um, so we looked at the R and we say this one is a set of real numbers. Set of real numbers. So R, the capital R is a set of real numbers. We just say R, just R. Now, if we have like two entries, if we have like two entries in a vector, like for example, if the vector A is equals to, let's say, 1 and 1. So this vector A is the element of real number, which has two entries, which is 1 and 1. Now, if we have three of them, so it means this is like 3 by 1. So it is like, no, sorry, 2 by 1. 2 by 1. If we have three of them, like let's say real numbers, if the vector is, let's say A is equals to 1, 1, 1, then there are three entries there. So we have three entries there. So this is actually 3 by 1. Now, if we continue like that up to Rn, then there are n entries. Let's say we have the vector B, which is equals to, let's say, B1 up to Bn. B1 up to Bn. So this is a vector which has n entries. So this is like n by 1, like n by 1. So that is it. Okay, now let's look at the properties of Rn, the vectors with n entries. Properties of Rn. Now, if we let the vector u, v, and let's say w, 0 vector to be the elements of Rn, and C and D to be the elements of real numbers. C and D are the scalars. So these are the scalars. Then property number one, u plus v, the vector u plus v is the same as if we add the two vectors. It is similar to adding the vector v plus the vector u. So it means this is commutative. So we can actually add u plus v, which is similar to adding v plus u. Number two, u plus v, the vector u plus v, if we add the two of them, and then we add the vector w, then it is similar to adding u plus v plus w. So it's similar to adding v plus w first, and then you add u. So this is associative. This is associative. Number three, If you add u, the vector u plus the vector 0, which has 0 entries, then it is similar to u. It is similar to u. And this one is actually additive identity. Additive identity. Number 4, u plus the vector u plus minus u. If we add the vector u and then you subtract u plus the negative u, then this is equals to 0 vector. And this one is actually additive inverse. So the inverse of addition is negative. Number 5, if we multiply the scalar u plus the vector v, it is similar to c u plus c v. C plus c. So this is actually distributive. This is actually vector distribution. You're distributing the vector by multiplying by the constant, which is the scalar. Number 6. If you have the 2 scalars here and then you multiply by the vector, then it is similar to c vector u plus d vector u. D vector u. So this is actually distributive also, but in terms of the scalar distribution. Number 7, if you multiply c by du, then this is similar to cd, cd. And this is actually associative, but this is in terms of the scalar. This one is in terms of the vector. That was associative in terms of the scalar. And then lastly, number 8, if we multiply 1 by u, then it is similar to u. And this is multiplicative identity. So if you multiply the identity, which is 1, 1, 1, 1, 1. So those are the properties of vectors addition. So in this course, mostly we will just be dealing with addition of vectors and scalar multiplication. Addition, which can be also addition, which is subtraction, and scalar multiplication. Those are actually the things that we'll be dealing with. So as you can see, just adding here, adding, and then you multiply by the scalar. You multiply also by the scalar, and this one is multiplied by the identity. So we will not be doing multiplication of vectors, like multiplying u by another vector b. No. Okay. Let's come to section 2.1, and in this section we're going to look at section 2, and we're going to look at vector equations and linear systems. and linear systems. So let's start from the first 2.1 and we look at definition. Let's look at the definition. Let's start from a vector equation. A vector equation. A vector equation in n variables, which are x1 up to x, let's say xp in n variables, which are x1, x2 up to xp, is an equation of the form x1, the vector a1 plus x2, the vector a2 plus xp multiplied by the vector ap is equals to b, the vector b. So the vector equation is an equation of that form, where x1, where a1, the vector a1, the vector a2 up to the vector ap are the elements of real number Rn. Elements of Rn. And b, the vector b, is also an element of Rn. Also an element of Rn. Now, a solution of a vector equation in p variables is a list S1, S2 up to SP of numbers such that the vector equation is true if x1 equals to s1, x2 equals to s2, up to xn equals to, or xp equals to sp. xp equals to sp. So those are the solutions. So if you want to get to the solution, then the solution is the same as equals to this variable, which we are looking for. The context is x and this. So this S1, S2 up to Sn are all the solution sets. So those are the solution sets. The solution sets. Okay, let's look at example. Let's look at an example. So we are at example number 2. Example 2 in this section. Now show that x1 equals to 2 and x2 equals to 1 is a solution of the following vector equation. And we have x1 multiplied by 2, 3, 5 plus x2 multiplied by -1, 2, -3 equals to 3, 8, and 7. Show that x1, x2 is a solution of the following vector equation. So let's look at the solution. So let's prove. Now, when x1 equals to 2 and x2 equals to 1, then x1, 2, 3, 5 plus x2, -1, 2, -3 is equals to 2, 2, 3, 5 plus 1, -1, 2, -3. And this is equals to 4, 6, and 10 plus -1, 2, -3. And this will be equals to what? So how do we add? So when we are multiplying by the constant, which is 2 here, then we distribute 2 inside in each one of those entries there. So the first one is 2, the 4, the first one, the second one is 6, and then 10. And then when we add the 2 vectors, then we get 3, we get 8, and then we get what? 7, which is equals to that. So it means x1 and x2 are the solution sets of that equation. So x1 equals to 2 and x2 equals to 1 is the solution of the vector equation. It's a solution of the vector equation. Okay, let's look at example number 3. Now, convert the following linear system to an equivalent vector equation. So if we have the linear system 4x1 plus x2 plus 3x3 equals to 9, x1 minus 7x2 minus 2x3 equals to 2, and then 8x1 plus 6x2 minus 5x3 equals to 15. So how can we convert that on the linear system? So this is a linear system. So we want to convert to the vector equation. So how can we convert that? So to convert this, then, so if this is the linear system, so we need to convert this one to now the vector equation. So the solution. So let's look at the solution. So how can we convert this? Now, here, this is similar to 4x1, x1, 8x1 plus x2 minus 7x2 plus 6x2, and then plus also 3x3 minus 2x3 minus 5x3, which is equals to 9 to 15. Are you seeing that? So it is similar to taking this plus this one, also including the minus, and then plus also this. Equals what? 9 to 9 to 10. Okay, so if you open this one back, then you can go. Now, we can now factor out the variable in each one of them. So when you factor out the variable here, then it will be x1 multiplied by the vector 4, 1, 8, plus x2 multiplied by the vector 1, minus 7, and 6, and then plus x3 multiplied by x3, 3, -2, and -5, and then equals to 9 to 10. equals to 9, 2, and 15. So this is now the vector equation. So that is the vector equation. Wait a minute. Any question? So make sure you check the signs. Okay, now it means that A1 is equals to 4, 1, and 8. So the vector A1 is equals to that. A2 equals to 1, -7, and 6. And then A3, the vector A3 equals to 3, -2, -5. And our B is equals to 9, 2, and 15. 9, 2, and 15. So therefore, our vector equation is the same as x1 a1, the vector a1, plus x2, the vector a2, plus x3, the vector a3, equals to what? Equals to b. Equals to b. So therefore, this is our vector equation, which is formed from our vector a1, a2, a3, and then our b. Now, to write this in augmented matrix form, then it means that we take these vectors here, all of these vectors here. So to write this linear or the vector equation into the augmented matrix form, then we can write this as, are we done writing this? Okay, so so it is actually equivalent to writing this as A1, which is 4, 1, 8, 1, -7, 6, and then 3, -2, and -5, and then 9, 2, and 15. So that is our augmented matrix, which is similar to A1, A2, A3, and then our B, which is similar to that. So that is our augmented matrix. So we can write. Any questions? Now let's look at example number 4. Example number 4. Now, convert the vector equation x1 a1 plus x2 a2 plus x3 a3 equals to b to equivalent linear system, where a1 equals to -2, 3, a2 equals to 8, 5, then a3 equals to 1, -6, and then our b equals to 0 and 0. So how can we convert that to equivalent linear system? How can we convert to linear system? So we know that, so the solution, so we know that the vector equation is of this form. So our x1 a1 plus x2 a2 plus x3 a3 equals to b is the same as bringing this now x1 -2, 3, plus x2, 8, 5, plus x3, 1, -6, equals to 0, 0, equals to 0, 0. Equals to 0. Then now we can take back the variables. So it is similar to -2x1, 3x1, plus 8x2, 5x2, then plus x3 minus 6x3 is equals to 0 and then 0, 0, and then 0. Right? Then finally, we can write this one as -2x1 plus 8x2 plus x3. And then here 3x1 plus 5x2 minus 6x3 equals to 0 and then 0. And finally, we can write this as -2x1 plus 8x2 plus x3 equals to 0, and 3x1 plus 5x2 and 6x3 equals to 0. And that is our any question up to that? So our augmented matrix of this linear system is similar to bringing this augmented matrix of this linear system is the same as bringing this -2, 3, 8, 5, 1, -6, and then 0, 0 here. So that is our augmented matrix. So which is similar to writing this as A1, A2, A3, and then our B. B then. Okay. So let's look at the remark. Each vector equation, x1 a1 plus x2 a2 plus xp ap equals to b is equivalent to linear system and the augmented matrix of the equivalent linear system. Is A1, A2, AN, and then so that is the augmented matrix of the equivalent linear system. So the vector equation and its equivalent linear system have the same, the solution. They have the same solutions. Okay, now let's come to section 3 in this 1.3. And this one is a linear combination of vectors. Linear combination of vectors. Linear combination of vectors. So let's start from 3.1, which is the definition, which is what is a linear combination. Linear combination. So an expression of the form, C1x1, or let's use V1, plus C2 V2 plus CP VP, where V1, V2 up to VP are elements of Rn, and C1, C2 up to CP and the vectors, which are the elements of real number, is called a linear combination of the vectors V1, V2, VP with weights C1, C2 up to CP. So that is the definition of a linear. So when we add, actually similar to the vector equation, but the other one was an equation. But this one is an what? An expression. So C1 V1 plus C2 V2, and V1 are the vectors in Rn, and C1 are the coefficients, which we call them the weights. So it forms a linear combination. Now, from the linear combination, then it comes now to the subspace of this linear. This is now coming to the next section, which is the subspace of the linear combination, which we can say the subspace of Rn. What is the subspace of Rn? So the subspace of Rn, if we let V1, the vectors V2 up to VP to be the elements of Rn, then the set of all linear combinations V1, V2, VP with weights in real number is called the subspace of Rn spanned by the vectors of V1 up to VP, which is written S the span of V1, V2, all the way to VP, which is equals to C1 V1 plus C2 V2 plus CP VP, where C1, C2, CP are elements of real numbers. So the subspace, which is a span of this, is so this span is just a collection of the vectors. So it's a collection of those vectors. So the subspace is just a collection of vectors, which is the span of vectors which are found here. So this span is actually similar to this linear combination where C1 is the elements of real numbers, which are the weights. So let's look at example number 5. Let's look at example number 5. Now, determine whether B is a linear combination of A1, A2, A3, or not, where A1 equals to 1, -2, 0, A2 equals to 0, 1, 2, and A3 equals to 5, -6, 8, which is, and our B equals to 2, -1, and 6. So determine whether A1, A2, A3 is a linear combination. So how can we determine this? So how can we determine this one? Now, to determine whether this one is a linear combination, then we need to write this in augmented matrix form. So we need to write in our augmented matrix form. So after writing it into the augmented matrix form, then we now reduce it. So we now reduce it. So once we reduce it, then we should be able to get the solution of that linear system. So to get a solution, that means the last row, once we reduce it, should not be contradictory. So if it is contradictory, then it means the linear system is not consistent. And if it is not consistent, then therefore, these vectors here are not linear combinations. That means we don't have the solution. So it means we don't actually have the solution. So how can we solve this? So the solution. So what we need to do is we determine whether x1 a1 plus x2 a2 plus x3 a3 is actually equals to b, is equals to b, is consistent or inconsistent. is consistent or inconsistent. Now, to determine whether this one is consistent or inconsistent, then we write this one in augmented matrix form, and then we reduce it. So we reduce it. So in augmented matrix form, then it will be 1, -2, 0, 0, 1, 2. Then we have 5, -6, 8, and then 2, -1, and then 6. 2, -1, and 6. Then we now reduce. So we now reduce. So they have already done for us this. So we now reduce the second entry in the first entry in the second row. So here it will be our new R2 will be R2 plus twice R1 plus twice R1. So in this case, then we have 1, 0, 5, and 2, and then we have 0, we have 1, we have 4, and then 3. And the last one is still the same, 0, 2, 8, and 6. Then we now reduce the 2 here. So to get the new R3, then it is R3 minus 2 R1. R2, sorry, minus 2 R2. R3 minus 2 R2. So once we reduce this, we have 1, 0, 5, and 2, 0, 1, 4, and 3, and then we have 0, 0, 0, 0. So what do you see from here? Is the last row contradictory? Is it contradictory? It is not, right? Because we don't have anybody. So we have actually have. So what are the basic variables here? So we have the pivot position here and here. So we don't have the pivot positions here. So it means x1 and x2 is our basic variable, and x3 is our free variable. So if we have the free variable, then it means we have infinitely many solutions, right? We have infinitely many solutions. So therefore, we are able to get a solution of this. So if we are able to get a solution of this, then it means that the linear system is what? Is consistent. So therefore, we can say, now, in this case, what we get is our x, if we write this one in linear system form, then it means our x1 plus 5x3 equals to 2, and x2 plus 4x3 equals to 3. And therefore, we take the values of x1 to the other side. So x1 equals to 2 plus 5x3, or x2 equals to 3. Is it plus or minus? This is actually minus. Minus 4x3. And then our x3 is what? Is our free variable. Or x3 is our free variable. So in this case, for what? For any x3. For any x3. So you can put any value of x3. So you will get the solutions of x1, x2, and x3. So you can say when x3 is 0, then x1 is 2, x2 is 3, x3 is what? x3 is 1, so you can put the value to get the solution of that linear system. So therefore, we have the solution here, then the linear system is consistent. And then, if it is consistent, so it means this A1, A2, and A3 are linear combinations for what? Of B. So now, if we have this, so we can say, if we take x3 to be equals to 0, if we take x3 to be equals to 0 here, then x1 equals to 2, x2 equals to 3, x2 equals to 1. If we take x3 equals to 0, then x1 equals to 2 and x2 equals to 3. Therefore, to check whether this linear system is actually the linear combination, then it means that here. So therefore, it means that our x1 is, so here, our x1, so we know that x1 A1 plus x2 A2 plus x3 A3 should be equals to what? Or B. So we have our x1 here is 2 A1 plus x2 is 3 A2 plus x3 is 0 A3 should be equals to what? Should be equals to B. Should be equals to B. So then 2, and then we have A1 is 1, -2, and 0, plus 3. A2 is 0, 1, and 2, plus 0, which will give us 0, of course, 5, -6, and 8. So what do we get here? So this is equals to, if we distribute 2 there, 2, -4, and 0, and then plus 0, 3, and 2. The other one is 0. So we have our 2 minus 4 plus 3 is -1, 0 plus 2 is 2. No, this is 6, right? So that is 6, and this one is 6. So we have 2, -1, and 6. So is that the solution of, is that equals to B? Yes, so it is equals to B. So it means that that is actually the linear combination. So it means A1, A2, and A3 are linear combination. Okay, now let's look at, oh, time's up. So let's see example number 6, and then we'll come and look at it next time we meet. So determine whether the vector B is a linear combination of columns in A, where our A equals to 1, -2, -6, 0, 3, 7, and then 1, -2, and 5. And our B equals to 11, -5, and 9. 11 minus 5 and 9. So here you just do the same thing. So you just reduce, see whether it is giving us the contradictory, or it is consistent or inconsistent. Once it is consistent, then it means it is a linear combination of that. Okay. So we can meet on Wednesday. I'll post the homework in Moodle.